Welcome to the 27th lecture video for Physics 4A. We return one last time to demonstrating additional mixed problem-solving strategies, including the methods we introduced for the oscillations and wave phenomena. While these exam questions will mostly focus on oscillations and waves, you still need to remember how to apply force analysis and conservation law problem-solving techniques as necessary. We start with a light review of what we have covered in the last 2 weeks and the free-form timed assessment demonstrations of questions titled Ballistic Pendulum 4, Standing Waves, and Rod, Sphere, Standing Wave. These demonstrations cover the exam type and level reasoning and problem-solving practices. This is the last of Mixed Problem-Solving Strategies lecture videos. In the remainder of this semester, we cover fluid mechanics and overall review of the semester, but we won't do a comprehensive review of problem-solving strategies such as what someone might prepare for a comprehensive final exam. Well, let's see what I forgot. So when you look at this set of topics, you will see that it includes the whole rotation. But a lot of things in rotation you won't have to worry about for exam 3, like the kinetic energy. It's going to be 0 because it'll be static equilibrium. Or rotational kinetic energy. But I think I actually trimmed out the things that you don't have to worry about. Okay, so those are together probably somewhere between 30 to 40% of the exam. And the majority of the exam is on oscillations and waves. So, well, what do you remember about oscillations? What did we cover what did we bring up as we were talking about oscillations and waves? I guess we could go in order of how we covered it, but I think it's better to, because this is exam review, not introduction of topics, it's better to cover in terms of things that are, I guess, more memorable, and actually, hopefully more memorable because it's important. Let's focus on oscillation. What do you remember about oscillation? What, I don't know, key terms or concepts do you remember being introduced as we are talking about oscillation? Steven? See here. Yeah, angular frequency is actually a big part. So let me just write that down as 1. And there are several things you can bring up as we are talking about angular frequency. Let me actually talk about this in a way that maybe wasn't what Steven was going to mention. This can be a jumping off point for a bunch of vocabulary terms that you should know. What's most closely related to angular frequency omega? Like what's another quantity that's most closely related to angular frequency? Frequency, yeah. You just take off angular and then you have frequency. So frequency is related to angular frequency, and you should remember all these relationships because the idea is that the question might give you an information in any of these related quantities, and you'll have to be able to work it back to angular frequency. So frequency would be usually use letter F, and that's equal to angular frequency divided by 2 pi. Or angular frequency is frequency times 2 pi. What else is related to angular frequency or frequency? Amount of time, there was actual word for that. Yeah, period. So we define period in connection with the angular frequency and frequency. So that would be, I don't know. I go back and forth between using capital T and P. Let me use capital T. So period is 1 over frequency. Any other vocabulary terms that are directly related to any of these 3? Amplitude, it does come up with oscillation, but it's independent of angular frequency. So
Let's handle amplitude first. Let me write it down. We are going to come back to it. So let me write down amplitude here. But amplitude has nothing to do with the angular frequency. In fact, that was one of the big thing about simple harmonic oscillator motion, right? For simple harmonic oscillator motion, what happens to angular frequency as you change the amplitude? Abdi? So imagine so pendulum is a kind of a simple harmonic oscillator motion. You know, it has a kind of angular frequency of motion. If I increase the amplitude, what happens to the angular frequency of motion? So this may sound like a trick question, but if you are prepared, it should not be a trick question. Anybody can answer? How is amplitude of simple harmonic oscillator related to frequency of, or angular frequency of the simple harmonic oscillator? Yes, Stephen? Yeah, they are not related. That's really the thing. If you're looking at how fast it's moving, then they are related, of course. But if you're looking at the frequency of motion, they are not related. In fact, so that's one of the things you should do. Now, the other set of things you should know about angular frequency, which are the formulas we derived by application of math. The two biggest set of formulas you should really memorize, have in your formula sheet, are the natural frequency of oscillation for meson spring and pendulum. So natural frequency, or natural, I guess it should be natural angular frequency of oscillation are for meson spring. So this is specific to the system you are talking about. If it's on meson spring, then this was the formula, square root of k over n. And I think we did a pendulum one, right? So if it's pendulum, it should be square root of g over L. Okay? Like these are formulas that are useful enough that you should have them memorized, or at a minimum have in your formula sheet. And what these formulas are telling you is that the kind of things that determine the oscillation frequency of a simple harmonic oscillator is that it's just a fixed property of the setup. Spring constant, mass of the mass, gravitational acceleration, and length of the simple pendulum. Like amplitude does not occur in it at all anywhere. Okay? So where would you be concerned with the amplitude then? What kind of things is amplitude related to? I mean, everyone here knows the definition of amplitude, right? How much it's being displaced. What other physical quantities can you relate amplitude to other than displacement? So with the pendulum, so you are seeing that as it swings, its height changes, right? So that will relate to a particular physical quantity because it's not always going to be height. If it's a meson or spring that's horizontal, then as it oscillates, height won't be changing. But there's some kind of physical quantity that's always associated in some way with amplitude. Isha? Maximum velocity is one. I want to get at a more central idea here, though. So it'll eventually relate to maximum velocity through this. So I guess I could write maximum velocity down here. But I want to max velocity. I want you to have a key to the most important quantity that relates directly to amplitude, or most closely with amplitude. Energy. So simple harmonic oscillation motion happens in a situation where energy is conserved. Amplitude describes maximum displacement. So this is the position where velocity is zero, kinetic energy is zero. This is the position where you have maximum potential energy. So as it oscillates, because energy is conserved, this potential energy changes to kinetic, back to potential, back to kinetic, back to potential. So you should remember the relationship, how energy is related to oscillation. So I'll just say amplitude relates to potential. But what I'm going to use this as a platform to mention is really you need to be familiar with energy in oscillation. How to express it, how it's expressed. It's kind of a review of what you have done for exam 2, you know. If it's mass on a spring, then it's, you know, spring potential energy. If it's pendulum, then you have to work out all the geometry stuff to, I probably won't give that, I don't know. But in an honors class, you might have done that. But so if we wanted, of all the things we introduced to dealing with oscillation, if we had to pick out one thing that relates most directly to energy, then it's going to be amplitude. Right? Okay, I gotta hurry up because I'm kind of running out of time. One very important aspect of oscillation and waves that you cannot forget, that you have to review, you have to make sure that you are not leaving behind, is it's the mathematical representation. So we talked about mathematical representation of oscillations and mathematical representation of waves. So you need to be familiar with those mathematical representations. So for example, if you're dealing with a wave, you might see something like this. Not wave. If you're dealing with oscillation, let's say oscillation of a mass on a spring moving up and down, then we could describe height of that mass as a function of time. And if I do that, I'm going to get an expression that looks like this. Let me write down all the different constant parameters in different color. So cosine is just a function, and time is a variable. So all those will be there, and plus. Let me write down some of the important constant parameters in different colors. Amplitude is one of them. You need to know how to find the amplitude of some oscillation. Angular frequency is another one. Given some sufficient information about the setup, you need to know how to find the angular frequency. And phase factor is the final one. Once again, given enough information, you need to know how to find the phase factor. There was actually a portable TA question in your homework that was actually walking through this exactly. I want you to know how to do it. I will test you at some point. If not exam 3, then final exam. Because you know, a good deal of what we do in this class is helping you make a sense of mathematical expression. Because in my experience, very few people learn to do that in their math classes. I wish you did it in math class, but if you didn't do it in your math class, you should do it at least here. So you know, when you have this expression written down, it's really easy to lose the meaning of what each of these have. And I want you to know how to find each of these, relate them to some physical aspect of the setup. And once you have this, then know how to use it. You know, use this to find the velocity, acceleration, that sort of stuff. And there's also the mathematical representation of wave. So this was for simple harmonic oscillator, and you do also have to know it for wave. So for wave, I'll just write it down. I'm running out of time. So wave is going to be a function of position and time. And I guess for the mathematical representation, at least to start, I want you to focus on the traveling periodic waves. Because with the traveling periodic waves, I can put it in a very particular standard form where you should know meaning of each of these colored parts. So let me write it out. So this function is going to be equal to some amplitude, I'll write it later, times some trigonometric function, cosine of, and then it's going to be a function of position and time, and there may be a phase factor. So let me put in all the important or quantities that have a particular physical meaning into colors. I hope I have enough. So let's start out with amplitude. You need to be able to associate that with something. let me do omega in the same color. So there's angular frequency omega, or frequency. You need to be able to relate that to something. And we have a new quantity. Let me do that in blue. Wave number k. You need to be able to relate to the other information that's given in the problem. And you have the phase factor. Oops, I already used the black. Let me do purple for phase factor. And there's one final aspect of all of this. The relationship between these two can be either minus or plus. You should know physical meaning for either of these two signs. So, it's all in one single expression. And with waves and oscillation, one single expression can pack a lot of information there. All right, so I have less than a minute left. Let me just write down the remainder of formulas that you have seen me lecture, and you should know. So you should know this relationship. The wave speed is equal to wavelength times frequency, right? I think we spent some time on that. And here's something that I don't think we spent a lot of time on, but it's a formula that I want you to know anyway. This is the part that I was hoping to get to today, but ran out of time. We can't get to it. So what do you remember about wave speed? Do you remember something about wave speed? What we mentioned about wave speed? It's some kind of constant, right? It's a property of medium. It's said here. It's property of medium. And what I want you to know in addition to that is how it is determined by the properties of the medium. So there aren't that many formulas for wave speed that I would want you to know. The one formula I want you to know is the wave speed for a wave on a string. And the formula for that is the square root of tension over linear mass density. There were some homework questions where there should have been homework questions where you had to know this to work out the rest. So you can look in the textbook for the derivation of this formula. This was the formula I was hoping to derive today, but ran out of time. So this is one formula you should know. In other circumstances, it's good enough for you to know that, remember, the wave speed is property of the medium, and I kind of have to tell you what that wave speed is. So wave on a string is one exception where I might give you the tension and the linear mass density, and I would expect you to know to figure it out. Let's see. I almost forgot to mention the most important thing that we just covered today. Wave interference phenomena. You should be familiar with the details of standing wave and beat. These are the two wave interference phenomena, either in 1 dimensions or 0 dimensions. Portable TA will have some examples of wave interference in 2D. We are not doing any of that in this class. You'll do wave interference in 2D in physics 4C if you take that. So, so with the waves, this is this is the biggest part of waves, right alongside the mathematical representation of wave. Good. Any questions? Okay, what did I forget? Let's make sure I didn't forget anything important. Oh yeah, I didn't mention all the vocabulary word, like wavelength and wave number. But feel familiar enough for those? Yeah. Oh, with the standing wave, there are nodes and antinodes. So this is a whole a case study topic. So make sure you read the relevant sections and you are not left empty. All right. Any questions? Comments? Okay.
So I am using a pool with a somewhat smaller number of questions. So I'll just do one and not reveal how small a pool I have, other than to say it is a pool. So given two different students, it is less likely than, or the likelihood is that two different people in class don't get the same question still, but it's a higher likelihood than before because my pool is so small. One thing that I will kind of warn you in case the question I get doesn't exhibit this, some of the questions might require you to use concepts from before, like with the conservation of energy and momentum or with the static equilibrium. So, I say mostly these chapters, and this is doing a lot of work, and earlier mechanics concepts as needed. Physics is cumulative subject. Just because the assessment is about oscillations and waves doesn't mean you can just forget about the previous mechanics concepts, which might get called in as needed. So with that, let me start. I genuinely don't know what I'm gonna get. I might potentially get, okay, yeah. So this question will involve a collision, as you can see here. And I think in the previous, not the immediate previous, but one dealing with the energy and momentum, you might have seen a similar ballistic pendulum question. This is along the same line, but you will see that it now has some parts that relate to oscillations and waves. More oscillations than waves. So a simple pendulum consists of a small mass m hanging at the, it's describing all that, comes in with the speed and collides after they are stuck together. Okay, that's important. So it's a completely inelastic collision, which will conserve momentum, but I won't use any conservation of energy. The pendulum swings back and forth. Okay. For each of the questions below, for the following three physical quantities, state whether or not they are conserved in this collision process. Okay. I see. Yeah. So total, I think I can just type an answer out here. So total mechanical energy is not conserved because this is sticking, also known as completely inelastic collision. And 2 is actually a little bit, it can be tricky. So I'm going to skip 2 for now and answer 3. So total angular momentum about pivot point is conserved, I think. Let me see here. Region messiness. Okay, I'll say this is conserved if the friction at the pivot is negligible. So I'm considering this picture here. A rod supported with a pivot here, and I have a mass here, another mass coming in and colliding. And as these two things collide, all the forces are internal forces, which means there are only internal torques. The only other forces that could potentially produce external torque are the one, gravitational force, but gravitational force is just downward here, not exerting any torque. And the other forces are forces at the pivot point. But if we are calculating the angular momentum about the pivot point, then the torque due to, as long as there aren't tangential forces at the pivot, as long as forces in the tangential directions are zero, there won't be any external force at the pivot that could change the applied torque and change angular momentum. That's what this portion, if the friction is negligible at the pivot, is about. Sometimes as you're answering the questions, especially as you go to higher levels, you might see that the questions don't spell out all the assumptions for you, because sometimes spelling out the assumptions might actually give away the answer. So when you see something like that, or when you feel like you are seeing something like that, do this: state your assumption and answer, make a reasonable assumption and answer based on your reasonable assumption. Yeah. And you could say, if friction is significant, then total angular momentum is not conserved. But that assumption would also make it fairly poor pendulum. So I deferred the second one, total linear momentum, because I think it's one of those cases where my gut reaction, my intuitive reaction would have said, as these two things collide and interact, I could have some kind of pivot force here, and this would be something similar to a normal force. So if I try to treat this collision as lasting a very short amount of time, this force could go up. And so that's the first thing I would think about. And if I think about it that way, I would answer, total linear momentum is not conserved because of the pivot force. Now, I might have said that as a matter of kind of intuitive answer, but I think in this particular case, this pivot force ends up being zero, especially if this rod is massless, which it says it is, the massless rod of length L. So really, in this entire assembly, the center of mass of that entire assembly is at where this small mass m is. So I think in this special case of this particular collision, the pivot force here ends up being zero. So to reflect what I would say is, okay, total linear momentum, or let me say it this way, it could have been that the total linear momentum is not conserved in this interaction because of the pivot force, which I'm saying was possible. But in this particular case with the massless rod, the pivot force ends up being zero during collision. Zero other than one needed to counter gravity. So the total linear momentum should be conserved. That is impulse due to net impulse due to net external forces equal to zero. So yeah, all right. How am I doing on time? All right, I gotta go faster. So assuming V naught is small enough that the subsequent motion can be approximated as a simple harmonic oscillator motion, calculate in terms of given quantities and symbols, and defining new symbols and introduce angular frequency of oscillation and amplitude of oscillation. So angular frequency is actually easy if you have a formula memorized. There's a formula for natural frequency of pendulum, which is omega pendulum is a square root of g over L. Am I using capital L in this case? Now, if you have it memorized like me, then great, use it. Now, if you don't, this is where you are allowed to use the fact that this is an open book assessment. So you don't want to do this with every single fact, but if there's a key formula that you know is in the textbook, you just don't remember what it is, then you can look it up there and use it. That's kind of what open book is for. And the amount of the time limitation you are given, it kind of assumes that you are using those resources as they become necessary. So yeah, I don't really need anything else because this is one of the kind of property of simple harmonic oscillator. that natural frequency of motion is a constant, doesn't depend on a lot of parameters. And amplitude of oscillation. So there are different ways to get at it. I think the way I would prefer to get at it is through the conservation of angular momentum. So what I can say is, so oops, I shouldn't have labeled it as A. It's B. So I'm saying in the collision, angular momentum or total angular momentum is conserved, which means the total angular momentum about this pivot point before the collision, that would have been this displaced or this lever arm, which is my L, lever arm times the momentum of the mass. So that we mv naught. This wasn't moving at all, so no angular momentum there. That's going to equal the final angular momentum after these two things stick and start to move together with some angular velocity omega. That would be I times omega. And I think I have enough intuition that this angular velocity will be the maximum angular velocity at this lowest point. And as it swings up, angular velocity will decrease to 0, and then it will come back down and swing back and forth like pendulum. So let me call this omega max. Okay, and the amplitude of oscillation. Oh, I should be careful here. It's just as a note, this omega here, what I'm calling angular velocity, make sure you don't confuse that with omega is equal to square root of g over L. In situations like this, I would be fastidious about calling this angular frequency, because these two things refer to two different angles. This refers to the phase angle. This refers to physical angle. It's one of the confusing things about pendulum motion. So when it says amplitude of oscillation, I think what it's looking for is a theta max. So there's a couple different ways to get at it. I have 8 minutes. Let me just use conservation of energy. So this is this handles the collision portion. And actually, so if I'm going to use conservation of energy, I think I'm better off using this expression for the final angular momentum, which is so I, which would be the total mass of the whole combined thing times the L squared, that's the rotation inertia of point mass, times the omega max, or what I would call V max over L. So one factor of the L cancels, this L cancels, and I get a result that might appear familiar. V max is equal to the ratio of the masses times the initial incoming speed of the mass. This kind of analysis you've done when you did ballistic pendulum. Now, what I want to consider is the second snapshot, where this whole mass has swung up to some height, and my amplitude of oscillation is given by this theta max. And I'm looking at the geometry here. So this delta H should be L, length of the entire thing, minus this portion of the thing, L cosine theta max. So the conservation of energy equation that I would set up is the kinetic energy in snapshot 1 here, which is 1/2 mass times V max squared, is equal to the potential energy,
at this maximum height. So, setting this as my height equals 0, which is kind of implied in how I'm setting things up. So potential energy in this snapshot 2, which is equal to mass times g times this height h. L minus L cosine theta max. So some things cancel. These cancel. I need to plug in an expression for Vmax. And I have, let's see, let me just look at the time. 5 minutes, okay. I think I have enough time to solve for it. Or let me just do it this way. Theta max can be solved by, so Vmax, which I have in my attached work, and divide by m plus n times V naught, plugging into equation 1/2 times V max squared is equal to g times L minus L cos theta max, and solving for theta max should give the amplitude. And when you imagine solving for theta max here, what you have is a bit of an ugly algebraic expression, because you should be solving for cosine of theta max and then and take arc cosine, and that'll give you an answer that's acceptable. There's an alternate way to do it that gives a simpler expression. What it comes down to is in the way it's been approached here, I'm not using any small angle approximation, and that actually makes things a little difficult. And unless I use this version of small angle approximation, the cosine of x is approximately equal to not just 1, but 1 minus x squared over 2. Unless you remember the second term, it's a little bit hard to use a small angle approximation here without making things disappear. All right, I got what, 2 minutes? No, 3 minutes and a half. Okay, I think that's enough time to actually write this out. So it says, what is the angle theta t that the massless rod makes with the vertical as a function of time? Yeah. So this is just asking you to remember mathematical expression for oscillatory motion. So I'm going to just use using theta max from above. In order to meet this condition, I need to use sine of omega t, and I should say theta is a function of time is theta max, the amplitude, times sine of omega times t, where omega is omega pendulum above. And I think that's it. I just want to do a quick mental check, make sure that this satisfies the conditions, this condition at t equals 0, that is equal to 0. And after this strikes, initially goes in the positive direction, just as sine of omega t first increases in the positive direction as it goes. And part D, how much time do I have? Oh, 2 minutes. Well, let me first write down the answer that I know, and then I will maybe try to derive it. So omega RMS is equal to omega max divided by square root of 2. It's one of those things where when you are dealing with a lot of oscillatory signals or not, this is one of those things that you might end up memorizing. Let me quickly derive it. I might run out of time as I'm driving it, but I think that'll be fine. So, my omega as a function of time is going to look quite similar to this because that's basically omega as a function of time is the time derivative of the angle. So, well, this could get confusing, but let me try to do this. Okay, the time derivative of theta max
times sine of, and I will carefully label this omega of the pendulum times t. And I have to be careful not to confuse this natural oscillation frequency with any other angular velocities in my setup. So when I take this derivative, it goes through here. And here I use chain rule. Take the derivative of the outside and then the inside. So I should get theta max. Derivative of the outside is cosine of omega pt, and the derivative of the inside is just omega p. So I have theta max times omega p times cosine of omega pt, and this is I'm going to choose to label this as my omega max. This is my amplitude in the oscillation of the angular velocity. So what I now need to do is basically this calculus thing, and with some judicious trig identities memorized, you can actually do that by hand, simply enough. If not, there's computer algebra system, there's Wolfram alpha. Let me just finish doing this by hand. So omega RMS is equal to square root of 1 over t, integrate from 0 to t, and this thing squared. So omega max squared times cosine squared of omega p t dt. All of this square rooted. All right. So when you're doing this integral, really the key challenge is here. And the trig identity that you need to remember to handle this part is the power reducing formula. The way I remember power reducing formula is actually by remembering the double angle formula. Cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. And this has two different ways it can be written. You can choose to rewrite one or the other using the Pythagorean theorem. So when you do that, you could either rewrite this as 2 cosine squared alpha minus 1, or 1 minus 2 sine squared alpha. You can verify that on your own time. And what I'm doing for power reducing formula is I'm working backward from one with the square to the one without square. So I think the version I need to use is this one, because I want to reduce the power of cosine squared. So solving this for cosine squared alpha, I have cosine squared alpha is equal to cosine 2 alpha plus 1 divided by 2. So this power reducing formula is what I need to make the correct substitution here. I need to, so identifying alpha as omega pt, I need to, so it's gonna end up being, let me just write a version here, cosine of 2 omega pt plus 1 over 2. So that's what I'm gonna need to write. I'm just gonna do an in place substitution. Cosine of 2 omega pt. And this might look complicated, but when you think about it, it's actually not too complicated. Mainly because this integral here, integral over a period of a cosine function. Actually, with this factor of 2, it's an integral over 2 periods. When you integrate a trig function over 2 periods, you get 0. The area under the curve of any sine or cosine function over an integral period is 0. So I'm just trying to get rid of that orange thing. Okay, good. So when you imagine doing the integral, this will just end up giving you 0. So I don't have to do the integral at all. So the only part where I am doing the integral is really this 1 over 2. That's a constant. So when I just do that integral, this will just end up giving me 1/2 t, and evaluating from 0 to period t. So when I do all that, let me just move this down so that there's room for me to write here.
So when you do this integral, it's actually pretty simple. So I have under square root 1 over capital T times, and I have all of this. All of these are just constants. So it'll be omega max squared over 2 times. Now I had this T. I'm going to be plugging in capital T and evaluate at the limit, capital T and 0. So when I do all that, I'll just have capital T, which will cancel out with this thing that was there for the purpose of averaging. So this is what the root mean squared value ends up being. Square root of omega max squared over 2. So square root of that gives me just omega max divided by square root of 2. So that's it. That's where my memorized formula comes from. So, by the way, I did this as a kind of a demonstration, as not necessarily doing the logistics demonstration. In that, as long as you're not doing this very close to midnight, where you might get kicked out as you're doing this, I mean, I guess even then, as long as you're not typing things in here, you are fine. So you basically worked out the answer before the time limit ran out. Then what you should do is make sure you put in the answer before the time limit runs out. In your work, you can organize it and then attach it after the time limit runs out. That's how the thing works. And what I'm demonstrating here is that the system totally allows you to do that. And because that 20-minute time limit is meant to be a tight amount of time, I'm totally not expecting you to both work out the answer and have a work that's organized. I mean, here even this is actually not as organized as it ought to be, but so kind of the things where you need to have a derivation, have a full step-by-step justification. Those details you can write it out after you've submitted an answer. So save work and continue, and that's it. Let's hope we don't get the same question another time. Okay, now it's a new question. So let me do this one. So it says standing waves on a string is one remarkable consequence of wave interference principle. You've seen it in the lab, and you've seen this demo in lecture videos. The picture below illustrates one example. Snapshots at two different moments. You can imagine one maximum position, another maximum position. Like this would be one moment, and then this would be the other moment. Are overlaid. Okay. For each of the questions below, um, if the standing wave shown above is shaking at a frequency of 6 hertz, okay. So I think it's good for me to just start sketching things out. So this is the standing wave that's shown, and I hope you have enough intuition from having seen different types of standing waves that this is not the fundamental harmonic. This is not the longest wavelength that could be on this medium with the boundary conditions of the nodes at the end point. So if we have, so let me start out with the longest wavelength, the standing wave. The longest wavelength standing wave will look like something that fits half a wavelength within this distance, because that's the longest distance you can have and still have nodes at the end. So that would be the some other frequency that also result in this. Oh, and I could have also gone to higher frequencies if I wanted to. But let me just they want three other frequencies. So let me do this. And the next higher frequency or shorter wavelength would be where there's an additional node in the middle. And that's the kind of the pattern that you see with the standing waves. When you're going from one harmonic to the next harmonic, the consistent thing you will find is the presence of additional nodes or additional antinodes if you want to count antinodes. Now, with that in mind, I think this is the next harmonic with the two notes, so I'm gonna skip that. They've already given us the frequency for this thing, which is 6 hertz, and we'll use that um, in the answering of the remainder of part A. So the skipping that, the next one would be one where I have 1, 2, 3 notes between the two endpoint notes. So something that looks like this. At some point, it should look like I'm just drawing sinusoidal waves of shorter and shorter frequency. Like at higher harmonics, it becomes harder to distinguish between like what's something that meets the standing wave condition versus what's just a random thing. So okay, now if they just asked me to show these shapes, I could have given this, but they are asking for other frequencies that result in standing waves. So I have some length, and let me just make this easy for myself. Even though the question doesn't give me the length of the medium, and I guess properly speaking, I should be numbering, labeling this like L for general stuff. I have a feeling the actual length doesn't matter. So I can just make it easy for myself and say, hey, my L is 1 meter. As long as, oh wait, yeah. As long as my final expression doesn't really depend on, meters, like quantities of length, I'll be fine. So, so in figuring out frequency of all these other harmonics, I rely on the expression that you have seen and used for the lab, the relationship that connects frequency, wavelength, and the and the wave speed. So wave speed is equal to frequency times the wavelength. With the pictures drawn here, I can actually write down wavelengths right now. I can say, oh, this what's here is half the wavelength. So the actual wavelength should be double that. So it's going to be 2m. Here, my wavelength is exactly the length of the medium. And here, my wavelength is half of the medium. And to wrap this up here, my wavelength here would be 2/3 of the medium. Yeah, so 2/3 and actually I guess yeah. Let me just leave that there. So with all these scenarios, it would be nice if we knew what the wave speed is. If we know wave speed from that and from knowing the wavelength, we can work out the frequencies where this thing should resonate. And that's where you use the information given for the question. And in this setup is where you know the frequency and the wavelength, so you can figure out what your wave speed is. Again, assuming that your length is 1 meter. If your length is some other distance, your actual value of speed will be different. So let me do 6 hertz times 2/3 meter. So 3 divided 6, 2 times 2. So it should be 4 meters per second. So for all these frequencies, I can just do, so solving this for f, f should be v over lambda. So take 4 divided by these numbers. So I would get 2 hertz, 4 hertz, 6 hertz, and then 4 divided by 1/2 would be 8 hertz. And I hope the pattern that you see gives you confidence that these answers didn't actually depend on this assumption of any particular length. If I somehow kept this as a a symbolic quantity, it would have canceled out in the algebra. Just assigning a random number just makes the algebra slightly easier. And that's all perfectly allowed as long as you realize what you're doing. So with that, yeah, I've already done all this. If you're solving problems the way I recommend, you'll have done all this work as you're solving it. So the frequencies, other possible frequencies are 2 hertz, 4 hertz, and 8 hertz, among others. I think basically all the even frequencies, because when you're starting out at 2 hertz, and all the harmonics will be multiples of those, so it will be multiple of 2 even. Okay, so when the endpoint is changed from fixed to lucent, right? Um, it changes the boundary condition, right? Yeah. So this is mostly a, I don't know, memory question. So if you remember the things you did for our standing waves lab, this should be super easy. In the sense that, from the pre-lab, you remember that this is the kind of setup that results in a node at this end that hasn't changed, and at the other end, where it's a frictionless ring, it becomes an antinode. It becomes much easier to move the string at this end, and this will be your antinode. Basically, whenever this portion of string moves up and down, it doesn't have to drag along something else that's to the right of it. That makes the boundary condition antinode. Um, so yeah, this is actually the first picture. This is the one that shows the longest wavelength. This distance of L fits only quarter of the wavelength, so it's the longest wavelength. And then and I can draw a few more. I guess so I can do the boring thing and just to go up each time, one at a time. So I have an antinode. I'm gonna have an antinode at this end, and so I need one more node somewhere. I'm trying to figure out where it would be. Okay, one more node somewhere here. And I'm trying to draw a sinusoidal wave. Starting like something that looks like a sine. It has to cross the axis at some point. That's gonna be my node, and then at the other end here, it'll be at the maximum if because it's an antinode this time. So yeah, this is the next thing. But it doesn't say 3 lowest frequencies. So I can do something more interesting than what I'm doing above. And I can basically do something like this. Um, I can just start a wave, just cross the axis willy-nilly, however many times. All I need to make sure is at the very end point, I end with the antinode. Like that's the only thing that's really required. And however many times so okay, this is a terrible drawing. Just imagine this is a regular looking sinusoidal wave, not squiggly line. But I can just count how many wavelengths fit here and work out what the frequency of this kind of randomly imagined standing wave is. So okay. No, it says find the. Oh, so I think it's assuming we will use the same value for the speed that we've used in previous question. So let me do that, because otherwise there's no way to answer the question. Kind of depends on a whole bunch of things, and we are also continue to use this as the numerical value of speed. We are also continuing to assume that the length of the medium is 1 meter, the arbitrary value I assumed in part A above. So okay, I think it's worth just going through each of the pictures and coming up with an expression for the wavelength. Wavelength here, again, this is a quarter of the whole wavelength. So flipping that around, the wavelength should be 4 times this, or 4 meters. That way I fit a quarter of it in 1 meters. Here, I am fitting 3/4 of wavelength. So the wavelength in terms of meters should be, it should have a quarter remaining. That's a little bit longer than a meter. So I think that's a 4/3 m. That's right. Uh, take 1 meter divided by 3 equal parts, multiply by 4. Yeah, that'll give me wavelength. Oh, here, okay, let me just count. I have 1 full wavelength, 2 full wavelength, 3 full wavelength, 4 full wavelength. So 4, plus 1/4. So 4.25 wavelength is equal to the length of the medium. So solving this for wavelength, I get that's 1 divided by 4.25. I'll do that in calculator times meter. Because it's going to be times L, but L is 1 meter. So okay. So for the frequencies, all I need to do is continue to use this formula. I will have a solved for frequencies V over lambda. So frequency 1 here is this speed divided by that, or 1 hertz. Yeah, that's lower than the frequency we had above. And frequency 2 here. And this is where you do have to be careful. It's not going to be double this because the boundary condition affects that pattern. It'll be 4 divided by lambda. Okay, 4s will cancel out. I'll get 3. 3 hertz. And here it's a frequency of whatever harmonic. I didn't carefully count, so I'm not sure. Now, if I do want to count, okay, so this was the second harmonic. So third, fourth, fifth, sixth, seventh, eighth, ninth harmonic is what's going to be. Now you can count the number of notes. That's a way to get to it, but not necessary. Let me just do 1 over 4.25 in a calculator. So I don't think I can. Wait, not 1, 4. 4 meters per second divided by 4.25. So that is 0.941 hertz. That doesn't sound right. What am I doing wrong? Oh, wait. I'm not dividing by this. I'm dividing by this, which means actually multiplying by 4.25. So 4 times 4.25, or divided by 1 over 4.25. Okay, so that gives me a sort of 17. Okay, that looks about right. 17 hertz. And there is a pattern here. I think the pattern is all the odd integer multiples of this. So 1, 3, 5, 7, 9, 11, 13, 15, 17. That's probably the pattern. So here, my answer should be frequencies of 1 hertz, 3 hertz, and 17 hertz are on resonance, and any other odd multiple of 1 hertz. Okay, let's keep going. Oh, wait, am I? I'm sorry, I spent too much time explaining. Okay, I've got 5 minutes. One striking feature is that explain the detail mechanics. Okay, I think I can just type it out here. So driving amplitude is small, but how do you build up a large amplitude? It's basically building up energy within the medium over many number of cycles. So on resonance, the driving force is at the exact right frequency to be adding mechanical energy to the system of oscillating string each cycle. So because this energy build up can happen over many cycles, even with a small driving amplitude, if the damping factors are small enough, large amplitude of oscillation can build up over time. So what's important is the over time part. When we are looking at these pictures, we are looking at a stable picture where energy taken up by damping is equal to the additional energy put in by the driving thing. In the simulation, I usually turn off the damping altogether, so something else weird happens. But let's not get into that. Yeah. Okay. One of the parameters is the amount of tension. If you wanna, so V is equal to square root of T over mu. To one of the formulas that's nice to have memorized. I think that's gonna be related because they mentioned the tension. T here is the tension. resonant gauge in A and B, if you want to keep the same shape of the standing waves while doubling the frequencies of resonances, how would you change the tension in the string? So we go back to the expression here. So frequencies of the standing waves, it depends on the wave speed. And before we got this wave speed, somehow, or I guess we assume the length. So exact values doesn't matter. What's relevant is that we want this frequency to increase by a factor of 2. And the wavelength won't change because this pattern won't change. So wave speed needs to change, increase by a factor of 2. So to double the frequency of the standing waves, we need to increase the wave speed by a factor of 2 from 3 over lambda in order to increase the wave speed by a factor of 2 without changing the linear mass density mu of the string. We need to increase tension force T by a factor of 4, so that after taking square root, it'll have increased the wave speed by a factor of 2. So yeah, that's it. Yeah, so this is it shouldn't be a difficult question. It's not meant to be a difficult question. So so yeah, I'm just gonna let the time run out and um, attach my work after the time runs out. Because I think if you were adding work while the time runs out, sometimes you can get kicked out. I don't want to deal with those situations. So let me just use this time to label A and B. And I think the C and D I gave enough answer here that I don't really need to attach additional work. Oh, not out of time yet. So yeah, this is the second of the questions in the question pool. And as I was saying, and as you have seen, there aren't that many questions in the question pool. There's a very good chance that you will see one of the 2 questions I have done. And if you're somehow unlucky and you get the other question that I haven't done, then do your best. Again, this is a super low stress, low anxiety item. Uh, what you get here, literally, very close to literally, won't change your grade. All right, once I start, I got 20 minutes. So let me get ready and start. Okay, I haven't done this question, so I'll go ahead and do it. So it says, consider a long thin rod with, okay, its radius is negligible, okay. So point mass there, setup is shown here, a very light rope is stretched, okay. Yeah, so it looks like a static equilibrium setup, which, that was last set. So there must be some wave part added here. So, but the first question is asking for tension in the rope, so we'll do that. Yeah, let me follow my own advice and draw separate free body diagram. I know there's a temptation to just copy this figure and start drawing forces on it, which you can, it's not all that wrong, but let me follow my own advice. So I'm following the standard strategy steps, starting with the free body diagram, and I'm starting with a kind of extended object because I need to indicate where the force is acting. So this rod has some mass, I think. The rod has some mass m uniformly distributed, and length L. So the gravity acting on the rod, it'll act like it's acting at the center of mass. So I have gravitational force mg acting on the rod, and there's a sphere at the end. So I'll have another gravitational force acting on the combination of sphere and the rod, capital Mg, and the rope, it's probably applying some tension force. So let me draw that tension force to the left. And as you're drawing this free body diagram, you should be asking yourself the question, did I draw all the forces? And here, given that acceleration should be 0, it should be quite clear to you that you didn't draw all the forces yet. And the remaining balance of the force, it's really going to be at the hinge, at the pivot point. There will be some kind of force there whose sole role is to make sure that net force adds up to 0. So unless we are being asked for the pivot force, net force equation won't tell us anything, because we have this force standing by here to make sure the static equilibrium condition is just enforced. So where it's asking for the tension in the rope, so in static equilibrium scenarios, you have two static equilibrium conditions to enforce, that net force is equal to 0 and net torque is equal to 0. This, as I said, won't really be useful because we have this unknown pivot force unless we are looking for it. Like this equation just serves to give us what the pivot force is. So we are just going to use the net torque equation with our center of rotation set up here, so that whatever the pivot force is, we don't have to know it, we don't care, we're not going to find it. So we only have to worry about the torque due to these 1, 2, 3 forces. So let me define the coordinate axis with respect to these forces. In terms of torque, defining coordinate axis amounts to deciding which direction is positive. I'm going to say clockwise it is positive. So the tension force, it's going counterclockwise, that's going to be labeled as negative. So that's one thing you need to do, and that's step number 2. Step number 3, we break down forces into components. I guess a version of that applies when you're calculating torque is figuring out the lever arm. So with the gravitational forces here, I'm just extending the line of action. These are the lever arms for mg and lever arm for capital Mg. And for the tension force, extending the line of action, this perpendicular segment is lever arm. I hope once you draw the lever arm lines, you can kind of see the triangular geometry. Are we given the angle? It makes a 60-degree angle with the floor. So we are given this angle theta. So once you have the angle and you got these these triangles identified, hopefully you have good sense of, oh, this is the trig relationship I should use for the lever arm for these forces. So let me just do everything in one shot. I'm going to go to step number 4, writing my net torque, Newton's second law equation, the net torque equation. My net torque is going to be, let me start with the gravitational force, the lever arm, this segment times the force, and this segment, I can see that is the adjacent side of a hypotenuse of length L over 2. So it'll be L over 2, lowercase, uppercase L over 2 times cosine theta, that's the lever arm, times mg. Okay, I can see that I'm going to run out of space, so let me move this over and have more space here. So that's one contribution to torque. I have a second contribution to torque from the other gravitational force. That's going to be the hypotenuse of L, adjacent side still, so it's going to be L cosine theta times capital Mg, and the tension force minus, it's going counterclockwise, and this lever arm. So I guess I'm going to try to identify this angle within the triangle. It's going to be this theta here, so it's the opposite side. And this length, I think I was given 2/3 of the way up, so it's going to be 2L over 3. So that lever arm will be 2L over 3 sine theta times the, let me zoom out a little bit, times the tension force T. And all of this, the sum of all the torque, they should be equal to 0. That's what the question says. How am I doing on time? I might have to go quite faster. So, okay, I have one equation, and I think I'm correct in saying that the tension is the only thing unknown here. So let me just solve for tension. I think the quickest way to do it is to move this term over to to the other side, that's 0, and multiply through by 3 over 2L times the sine theta. So after I've done that, what you should get is, I'm just going to do that in my head. T is equal to 3 over 2L sine theta times L over 2 cosine theta mg plus L cosine theta big mg. Let me do a little bit of factoring, a little bit of simplification. L's cancel, that's nice. And I think I can factor out cosine theta g from both terms. And that'll, let me just put the term together first. I have 3 cosine theta g over 2 sine theta times small m over 2 plus big M. And just one last bit of simplification, I can write sine over cosine as tangent theta to get 3g m over 2 plus big M divided by 2 tangent theta. Interesting. I don't know if I might have expected that, or well, tension is equal to 3 times g times m over 2 plus m divided by 2 times tangent theta. As theta goes to 0, t goes to infinity, I guess that makes sense. Okay, let's see. Suppose that so this is the wave part. Setting up standing waves on the rope. What are the frequencies of these standing waves on the rope? Oh, okay. I think from that picture, so let me actually copy that picture now. From the picture, I can, the thing I can get easily is the shape of the standing waves. So, for part B, 11 minutes. I got 3 more parts. Okay, I'll have to go a little bit more quickly. So, what I can get easily are the shapes of standing waves. And what I can tell you is the one with the longest wavelength will look like this. The one with the next longest wavelength will look like this. You know that both ends, and so on. So my longest wavelength, that wavelength will be this length here. Let me call that capital D times 2. And the next one will be D. And just working out the geometry in my head, I know this is 2L over 3, and this is theta. So the adjacent side, this is the expression that should hold. D should be 2L over 3 cosine theta, which means the first wavelength there will give me something like a 4L over 3 cosine theta, and so the rest I can get from harmonics. So it's one of the 3 lowest frequencies or the 3 longest wavelengths. So once I have wavelengths, that I can get the frequency from this relationship. Frequency is working at the units, 1 over second. So it's gonna be the speed, wave speed divided by the wavelength. Now, here's a formula that you kind of need to have memorized, or at a minimum know how to look it up in a textbook. Wave speed of wave on string is given by this formula, by square root of tension divided by what's called the linear mass density. Is that annoying? Oh yeah, they give you the linear mass density. That's great. So we worked out the tension, which means, so I'm gonna just write this down. V is equal to square root of T divided by mu. I'm treating T as a known quantity because I worked it out in A above. Where T is same as in A. And given this V, I can write down the expression for frequency. Frequencies are F equals V over lambda. And I'm just going to describe the 3 longest wavelengths. 3 longest wavelengths, giving 3 lowest frequencies are lambda 1 of 4L over 3 times cosine theta lambda 2 is, it's going to be half of that, 2L over 3 times cosine theta, and lambda 3 will be a third of the fundamental wavelength for, well, theta. Work through the relationships for f and v for frequency values. Just gonna leave it there. This gives all the necessary information. The answer is in terms of known quantities, at least known in theory. Okay, 7 minutes. There were some approximations made in order to give an answer in a moving very small. Make the approximation explicitly. Imagine the. So this is trying to give a hint. One of which is that I assumed that the tension force is the one calculated in A. Maybe if the string is plucked hard, the tension force will change. Maybe not. Especially if the rod vibrates enough. Possibly. How many do I need to give? Short list of things that might happen due to a large amplitude oscillations. With a large amplitude, the string might break. I think I asked for a short list, hoping to get at least this answer. But this is actually an open-ended question. There's no necessarily wrong answer. It's just brainstorming, which is not the best kind of question when it's a time limited. Okay, 6 minutes. Let me see what's D. Rope might break. Okay. Is there anything else? We'll come back later. Okay, if the rope breaks, okay, then what is the rod's angular speed immediately before it crashes? Okay, so I am going to assume that the rod and sphere are at rest the moment the string breaks, which might not necessarily be a good approximation, but that kind of allows you to do the calculations. So we are going to have to use conservation of energy, using conservation of energy. And let me see how much time I have. 5 minutes. Yeah, I think I have enough time to set it up. So for part D, we are going from the rod being in this position to the rod falling down, so that it's going to end up in this position. Label these snapshots 1 and 2, and I have a sense energy is conserved, so I'm going to use conservation of energy. Say that total energy in snapshot 1 is equal to total energy in snapshot 2. So I'm going to track the rod and the sphere separately, so they will have their own gravitational potential energy. So in position 1, I have the gravitational potential energy of rod, gravitational potential energy of sphere, and the kinetic energies are going to be 0. So I won't write them down. In the snapshot 2, I will set my y is equal to 0 here, so I don't have to worry about gravitational potential energy here. Instead, what I'll have is kinetic energy. And let me use rotational kinetic energy of the rod and the rotational energy of sphere separately. And I'm gonna make them rotate around this center of rotation, an actual fixed point. So with that, let me write down the expressions. The gravitational potential energy of the rod, I use the height of the center of mass, so it'll be mass of the rod times g times the height of the center of mass, which will be L over 2 times sine theta for the height, plus the sphere, capital M times g, L times the same sine theta. That should equal to the kinetic energy you get, 1/2. So the rotational kinetic energy is 1/2 rotation inertia times omega squared. So rotational inertia of a rod spun about its end is 1/3 ml squared. I have it memorized. If you don't have it memorized, then you'll have to spend some time looking it up, times omega squared, plus, they're going to have the same angular velocity because they are moving together as a rigid body. Sphere, I'm going to treat it as a point mass. It'll have rotational inertia of ml squared, mass times distance from the center of rotation. So, okay, I have this expression. So I'm going to do this. First, to type up the equations. We solve for the following conservation of energy equation. M times G times L over 2 times sine theta plus N times G times L times sine theta is equal to 1/2 times 1 ml squared over 3 times omega squared plus 1/2 times ml squared times omega squared. Solve for the omega in the following. So can I do this in my head? Possibly. So doing this, you get omega is equal to so mgl. Yeah, I'm just gonna write down the version that's not simplified, so that I can do this. This is the version that I can do in my head without writing anything down. That's the numerator. Denominator is gonna be ml squared over 6 plus ml squared over 2, and all of that is going to be square rooted. That's capital M. So yeah, I don't think it even really simplifies that much anyway. So in the remaining time I have, 1 minute, I can simplify a little bit, and the little bit that I will simplify is simplifying a little. You can cancel out the additional factors of L. So there's one factor of L that can get canceled out. So it'll be, L's gone there. So you have like divide by 2 here for mg over 2, and that's gone, and that L's gone. I think that's it. You can factor out sine theta, but g sine theta, and that's just about it. You could factor out g times sine theta. That'll give you that. It looks slightly simpler maybe, but not very much so. I think that's it. All that you can simplify. And I'm probably out of time too. Close enough. So yeah, and I don't think there's any more that was in my list. I'm thinking, and I don't know, in 10 seconds I don't think I'm gonna come up with something that I haven't come up with before. So that's the time. Let me just attach my work. So this was like half of it was actually topics that you have seen before, static equilibrium, and actually conserved rotation, rigid body rotation. And at this point in the semester, if you see something like that, that should not surprise you. Now, I won't ask you questions that are purely composed of formerly covered topics, because we are not doing cumulative final exam, and I'm not doing a backdoor cumulative final exam. But you can't forget what we covered before, because you might get a related question where a good portion of the question relies on you to those previous knowledge. So, all right, that's everything, and we can check the answer key to make sure that I didn't make any mistakes. Oh wait, we can't check the answer key right now, and it's not under this account because test student like you doesn't get access to the answer key while within the before the due date. So let me go into my instructor account and bring up this exact thing so that I can show you the answer key using the instructor account. Okay, here it is. So here's test student's results. answer key, and or the attached work, and I can bring up the answer key as the instructor. So it goes through all that, and I work out square root. Oh, I guess yeah, sine tangent theta. Yeah, we can write it out. Let me see. So this is the version with tangent theta 3/4 times. I think that's equivalent to that. Yeah. So okay, good. Other than forgetting theta was given numerically, that looks fine. And yeah, so in the answer key, I'll have worked out actual final expression. Or I didn't really. Yeah, because plugging in t actually doesn't simplify anything. That's why we are just saying, oh, use the t from above, and the rest of it should. Right. I still forgot about the cosine theta being given. 2L over 3, or the 4L over 3 cosine theta, that's the wavelength. Yeah, with the cosine theta being 1/2. I think that's right. And so I don't know, within the model answer, tension might change. Oh, I forgot. Yeah, the length might change, especially if the rod is moving. The moving rod will cause the length of the thing to change. So yeah, that's a possibility. But it's an open-ended question. So don't think of this as a closed list of correct things. There might be other possibilities that I didn't think of. And here, yeah, pretty sure. Yeah, so the solution probably plug in the value of theta, or not. So square root of g over, oh yeah, I could have factored the L out of denominator. Yeah, square root of g over L times the numerator. So I think this version here multiply top and bottom by 2 to get 2m there, and sine theta is stuck with that, and m over 3 plus, yeah, I think that looks right. So yeah, that's the that's the answer. And so again, here, the reason this question is in this set is, like in the previous free-form timed assessment, I couldn't ask you this question. That's why it had to wait until waves and oscillations chapter 2 be asked.